A quark-gluon plasma or quark soup is a state of matter in quantum chromodynamics which is hypothesized to exist at extremely high temperature, density, or both temperature and density. This state is thought to consist of asymptotically free quarks and gluons, which are several of the basic building blocks of matter. It is believed that up to a few milliseconds after the Big Bang, known as the Quark epoch, the universe was in a quark-gluon plasma state. In June 2015, an international team of physicists have produced quark-gluon plasma at the Large Hadron Collider by colliding protons with lead nuclei at high energy inside the supercollider's compact muon solenoid detector. They also discovered that this new state of matter behaves like a fluid. The strength of the color force means that unlike the gas-like plasma, quark-gluon plasma behaves as a near-ideal Fermi liquid, although research on flow characteristics is ongoing. In the quark matter phase diagram, QGP is placed in the high-temperature, high-density regime, whereas ordinary matter is a cold and rarefied mixture of nuclei and vacuum, and the hypothetical quark stars would consist of relatively cold but dense quark matter. Experiments at CERN's superproton synchrotron first tried to create the QGP in the 1980s and 1990s. The results led CERN to announce indirect evidence for a new state of matter in 2000. Current experiments at the Brookhaven National Laboratory's relativistic heavy ion collider on Long Island and at CERN's recent Large Hadron Collider near Geneva are continuing this effort by colliding relativistically accelerated gold or lead with each other or with protons. Although the results have yet to be independently verified as of February 2010, scientists at Brookhaven RHIC have tentatively claimed to have created a quark-gluon plasma with an approximate temperature of 4 trillion Kelvin. As already mentioned, 3 new experiments running on CERN's Large Hadron Collider, on the spectrometers ALICE, ATLAS and CMS, will continue studying properties of QGP. Starting in November 2010, CERN temporarily ceased colliding protons, and began colliding lead ions for the ALICE experiment. They were looking to create a QGP and were expected to stop December 6, colliding protons again in January. A new record-breaking temperature was set by ALICE, a large ion collider experiment at CERN on August 2012 in the ranges of 5.5 trillion Kelvin as claimed in their Nature PR. General introduction. Quark-gluon plasma is a state of matter in which the elementary particles that make up the hadrons of baryonic matter are freed of their strong attraction for one another under extremely high energy densities. These particles are the quarks and gluons that compose baryonic matter. In normal matter, quarks are confined. In the QGP, quarks are deconfined. In classical QCD, quarks are the fermionic components of mesons and baryons, while the gluons are considered the bosonic components of such particles. The gluons are the force carriers, or bosons, of the QCD color force, while the quarks by themselves are their fermionic matter counterparts. Although the experimental high temperatures and densities predicted as producing a quark-gluon plasma have been realized in the laboratory, the resulting matter does not behave as a quasi-ideal state of free quarks and gluons, but, rather, as an almost perfect dense fluid. Actually, the fact that the quark-gluon plasma will not yet be free at temperatures realized at present accelerators was predicted in 1984 as a consequence of the remnant effects of confinement. Relation to normal plasma. A plasma is matter in which charges are screened due to the presence of other mobile charges. For example, Coulomb's law is suppressed by the screening to yield a distance-dependent charge, i.e., the charge Q is reduced exponentially with the distance divided by a screening length alpha. In a QGP, the color charge of the quarks and gluons is screened. The QGP has other analogies with a normal plasma. There are also dissimilarities because the color charge is non-abelian, whereas the electric charge is abelian. Outside a finite volume of QGP, the color electric field is not screened, so that a volume of QGP must still be color neutral. It will therefore, like a nucleus, have integer electric charge. Theory 1. Consequence of this difference is that the color charge is too large for perturbative computations, which are the mainstay of QED. As a result, the main theoretical tools to explore the theory of the QGP is lattice gauge theory. The transition temperature was first predicted by lattice gauge theory. Since then, lattice gauge theory has been used to predict many other properties of this kind of matter. The ADS-CFT correspondence conjecture may provide insights in QGP. Moreover, the ultimate goal of the fluid-gravity correspondence is to understand QGP. The QGP is believed to be a phase of QCD which is completely locally thermalized and thus suitable for an effective fluid dynamic description. Production. The QGP can be created by heating matter up to a temperature of 701220000000002 times 1012 K, which amounts to 698928038052250000175 MeV per particle. This can be accomplished by colliding two large nuclei at high energy. Lead and gold nuclei have been used for such collisions at CERN SPS and BNLRHIC, respectively. The nuclei are accelerated to ultra-relativistic speeds and directed towards each other, creating a fireball, in the rare event of a collision. Hydrodynamic simulation predicts this fireball will expand under its own pressure, and cool while expanding. By carefully studying the spherical and elliptic flow, experimentalists put the theory to test. How the QGP fits into the general scheme of physics. QCD is one part of the modern theory of particle physics called the Standard Model. Other parts of this theory deal with electroweak interactions and neutrinos. The theory of electrodynamics has been tested and found correct to a few parts in a billion. The theory of weak interactions has been tested and found correct to a few parts in 1,000. Perturbative forms of QCD have been tested to a few percent. In contrast, non-perturbative forms of QCD have barely been tested. The study of the QGP is part of this effort to consolidate the grand theory of particle physics. The study of the QGP is also a testing ground for finite temperature field theory, a branch of theoretical physics which seeks to understand particle physics under conditions of high temperature. Such studies are important to understand the early evolution of our universe. The first 100 microseconds or so. It is crucial to the physics goals of a new generation of observations of the universe. It is also of relevance to grand unification theories which seek to unify the three fundamental forces of nature: expected properties, thermodynamics. The crossover temperature from the normal hadronic to the QGP phase is about 698928038052250000175 MeV. This crossover may actually not be only a qualitative feature, but instead one may have to do with a true phase transition, e.g., of the universality class of the three-dimensional Ising model, as some theorists say, e.g., Fridtjof Koch and co-workers from the University of Bielefeld. The phenomena involved correspond to an energy density of a little less than 7001000000000000001 GeV, FM3. For relativistic matter, pressure and temperature are not independent variables. So the equation of state is a relation between the energy density and the pressure. This has been found through lattice computations, and compared to both perturbation theory and string theory. This is still a matter of active research. Response functions such as the specific heat and various quark number susceptibilities are currently being computed. Flow. The equation of state is an important input into the flow equations. The speed of sound is currently under investigation in lattice computations. The mean free path of quarks and gluons has been computed using perturbation theory as well as string theory. Lattice computations have been slower here, although the first computations of transport coefficients have recently been concluded. These indicate that the mean free time of quarks and gluons in the QGP may be comparable to the average interparticle spacing. Hence the QGP is a liquid as far as its flow properties go. This is very much an active field of research, and these conclusions may evolve rapidly. The incorporation of dissipative phenomena into hydrodynamics is another recent development that is still in an active stage. Excitation spectrum. Does the QGP really contain free quarks and gluons? The study of thermodynamic and flow properties would indicate that this is an oversimplification. Many ideas are currently being evolved and will be put to test in the near future. It has been hypothesized recently that some mesons built from heavy quarks do not dissolve until the temperature reaches about 698956076177045000350 MeV. This has led to speculation that many other kinds of bound states may exist in the plasma. Some static properties of the plasma constrain the excitation spectrum. Plasma hypothesis. Since 2008, there is a discussion about a hypothetical precursor state of the quark-gluon plasma, the so-called plasma, where the dressed particles are condensed into some kind of glassy state, below the genuine transition between the confined state and the plasma liquid. This would be analogous to the formation of metallic glasses, or amorphous alloys of them, below the genuine onset of the liquid metallic state. Experimental situation. Those forms of the QGP that are easiest to compute are not those that are easiest to verify experimentally. While the balance of evidence points towards the QGP being the origin of the detailed properties of the fireball produced at SPS, in the RHIC and at LHC, this is the main barrier which prevents experimentalists from declaring a sighting of the QGP. For a summary, see 2005 RHIC assessment. The important classes of experimental observations are single particle spectra, strangeness production, photon and muon rates, elliptic flow, jet quenching, fluctuations, Hanbury-Brown and Twiss effect and Bose-Einstein correlations. In short, a quark-gluon plasma flows like a splat of liquid, and because it's not transparent with respect to quarks, it can attenuate jets emitted by collisions. Furthermore, once formed, a ball of quark-gluon plasma, like any hot object, transfers heat internally by radiation. However, unlike in everyday objects, there is enough energy available that gluons collide and produce an excess of the heavy strange quarks. Whereas, if the QGP didn't exist and there was a pure collision, the same energy would be converted into even heavier quarks such as charm quarks or boson quarks. Formation of quark matter. In April 2005, formation of quark matter was tentatively confirmed by results obtained at Brookhaven National Laboratory's Relativistic Heavy Ion Collider. The consensus of the four RHIC research groups was that they had created a quark-gluon liquid of very low viscosity. However, contrary to what was at that time still the widespread assumption, it is yet unknown from theoretical predictions whether the QCD plasma, especially close to the transition temperature, should behave like a gas or liquid. Authors favoring the weakly interacting interpretation derive their assumptions from the lattice QCD calculation, where the entropy density of quark-gluon plasma approaches the weakly interacting limit. However, since both energy density and correlation shows significant deviation from the weakly interacting limit, it has been pointed out by many authors that there is in fact no reason to assume a QCD plasma close to the transition point should be weakly interacting, like electromagnetic plasma. That being said, Systematically improvable perturbative QCD quasi-particle models do a very good job of reproducing the latest data for thermodynamical observables, including the aforementioned significant deviation from the weakly interacting limit, down to temperatures on the order of 2 to 3 times the critical temperature for the transition.